Okay, so I'll start. Today I want to discuss two different perspectives on the calculation that we've done so far, which is the calculation of the entanglement entropy associated with an interval in a 2D CFT. So let me start with a replicated target space perspective. This is perspective on this calculation, which will involve twist fields. Okay, and so the second perspective will be in terms of a thermal entropy. But first, let's do this target space perspective. And so let's repeat the setup. We're looking at a 2D CFT. So some theory with some Lagrangian for fields phi with coordinates x and Euclidean time that run over the complex plane. Okay, so I used either x and TE, or at some point I used complex coordinates zeta and zeta bar. Okay. So this notation now just refers to the fact that x and TE are running over the plane, and so I'll refer to this as the world sheet of our theory. Okay. So this is a theory with some Euclidean path integral, which is equal to the trace of rho equal to this thing. Okay. So basically, there are two ways of interpreting this n-fold replicated system. So this z of n, if this is z of 1, to calculate the entropy, we needed to construct an n-fold description of our system. And so we made that by taking different copies of the reduced density matrix. So starting with 2 and then extending it to n, and then taking the trace to get what we defined as this object z of n. Okay, you remember? And so the first way that we interpreted these objects was in terms of copying the geometry into this replicated manifold, right? So let me remind you of that. Actually, let me go already to the next board. So this is all just repetition, but I'm reminding you because I'll give you an alternative interpretation now, okay? So we wrote the squared of this reduced density matrix as such, where we glued together this piece and this piece by gluing over a dummy field phi tilde, okay? And so that led, if you do this n times, then that leads to this replica manifold that we drew, where the slits are connected as such, and then this one to this one. So in formula form, what we have here is the Euclidean path integral. So dx dte are Lagrangian running over fields, x and te. Where you path integrate over this complicated geometry now, which we call the replica manifold. Right? Okay, so far so good. In this notation, that means that now this n-fold replicated system is the same Lagrangian we had before. So before as in meaning the same Lagrangian as our setup, which is up there. So of our 2D CFT, but now on a more complicated geometry. So this is now our world sheet, okay, for this n-copy version of the system. Good, so in this language, what we did before is a world sheet perspective, where our coordinates x and te are continued from living on one copy C to living on n copies connected into this replica manifold. So our coordinates are continued to live on a replicated world sheet, which is our replica manifold. Good. Now I'll need some space, so I go to the middle board, for the second perspective on the same construction, okay? The second perspective is that you do not copy your geometry, you copy your field content, okay? So that's the target space perspective. So what do I mean by that? So we have the same picture for the squared of the reduced density matrix. Well, let me not write this line. This is confusing. Okay. We have the same picture in the sense that we still have two copies. But let me think of these two copies as one being the original system, but I'll rename my fields phi as being phi ones, the first set of fields phi. And here in this copy, I'll consider, so let's make some place. The same Lagrangian, but for a second set of fields, which I'll now call phi 2, again living on the complex plane. Okay. And I still need this condition. Here, the gluing condition was imposed as gluing this geometry actually together. Now, the gluing condition can be read as a condition on how these sets of copied fields are talking to each other. And so the gluing condition now is that phi 1, of course, it's the same gluing condition, but with a different interpretation, is that the field configuration of this first set of fields here, so the phi 1s at 0 plus, so this top line in the first copy for x in the interval A, this should be equal to the field configuration at t is 0 minus on the lower line here and x in A of the second set of fields phi 2. Okay? So this is now my gluing condition. I might actually already start on the next board. Well, okay, let's start here. Okay, so let's do this n times now to construct the n-fold replicated structure, which will give us z of n, okay? So for z of n, we now construct n copies. In each of those, you have the special points x1 and x2, which are the endpoints of your interval A, okay? But now you think of each of those copies as Lagrangians of one copy of the set of original fields on still the same geometry, the plane, okay? So each of these is C and then a Lagrangian of a copy of the set of fields. So here we have lambda of phi n, okay. Okay. With all those boundary conditions, so now I have n of these. So let me use a color. So the boundary conditions, now I don't have a very good visual presentation of it. I'm just going to add to the figure that I shouldn't forget there's boundary conditions, which means I have to specify how these different sets of fields are talking to each other. So the boundary conditions in formula form are just the extension of this. So I have phi 1 should be equal to phi 2 along A. Phi 2 should be equal to phi 3. Okay, and of course we keep going until we have phi n, which should be equal again to phi 1. Okay. So in formula form, okay, let me write that here. So in formula form, what I have is the following path integral, okay? So this now on the left is a formula form for that picture there on the right, for the same object that we've been discussing all this time, this z of n. So you see that this path integral is different, different interpretation than this path integral. Here you had the original theory with just one set of the fields, but you're path integrating over a replicated worldsheet manifold. Here, instead, you copy your set of fields into n of those, and you path integrate over just the original worldsheet, but including these boundary conditions on how the fields talk to each other. Okay? Now, okay, let me just write this new Lagrangian as 1 Lagrangian Ln for n different fields. Okay, this is just a definition now for rewriting the exponent in one notation. That corresponds pictorially to not bothering to write n of these copies, but write the whole thing as one copy C. There's an x1 point and an x2 point. At the moment, they are just referring to a point in the geometry where A is. Okay, so I have C and one full Lagrangian with n different sets of fields living on this C. Okay. Plus all the boundary conditions. So I have to add this to my figure as such because, okay, I don't know how to draw this, these conditions on the fields. Okay. So the second visualization on the right is just in formula form. It's just having introduced the notation lambda n of n fields. Okay. So this whole interpretation of the gluing condition is now a target space perspective compared to the worldsheet perspective that we did before, okay? So when here we had a worldsheet perspective, now we have a target space perspective on the gluing, which means that the gluing conditions are interpreted as being imposed on the field content of a replicated target space theory. So here we had a replicated worldsheet because we were talking about the coordinates. And here we have a replicated target space interpretation because we're talking about the fields, okay? Okay, so our new interpretation of the same object Z of n has a global symmetry under changing the fields phi I to phi I plus 1. So this is a Zn permutation symmetry of your setup, which previously was visible at the level of the geometry, that you could go from one sheet to the next and have a permutation symmetry there. Now it's a global symmetry of the setup in terms of fields, okay? Field symmetry. So, but the point is that this global symmetry can be implicitly implemented by placing so-called twist fields at the boundary points of your interval. So what that allows me to do is leave out in my picture these plus boundary conditions to remember, and just take the final picture that we were working with. So we had one sheet, but with a replicated theory on it. So instead of having to add here now plus boundary conditions, I'm going to place some fields here, and I'm going to consistently use crosses to refer to twist fields. I place some type of twist fields here, which I define to have this this effect of imposing these boundary conditions, or how these fields talk to each other. Okay. So let me write that in formula form. So I'm integrating all my n types of fields, I is 1 to n, over C. I don't need to add that I have these extra conditions, because I just introduce two fields, one sitting at each endpoint of the interval, so, as you remember, if you put in these path integral pictures, if you insert an operator, they appear in your formula here under the in the path integral. Okay, so I'm adding here two fields, Tn at position x1 and a Tn tilde at position x2. So, mathematically speaking, these appear here under the path integral. And these impose the boundary conditions because by prescription, Tn is a field that if one of the fields circles it, it transforms in, so if phi 1, for example, circles it, it will transform into phi 2. Okay, I'll make a picture. So if you have T sitting here at x1, and you have a field phi I of x, when that field turns around the twist field, it transforms into phi I plus 1 of x. Okay. And the other one is an anti-twist field, which transforms you to the I minus 1, I don't know, yeah. Transforms you in the previous phi. Okay, so the whole point is, of course, that you mimic the discussion that we had before, but using now a target space instead of a worldsheet perspective. Okay. And so if you've done this, okay, so let me repeat the last version of the formula. Just as a formula, you'll remember that this is a correlator. If you have operators in your, inserted in your path integral, this is just a correlator, so we can write this as the correlator of twist field here at x1 and twist field here at x2. And this correlator is evaluated in the theory, which has C as worldsheet and this lambda n as Lagrangian. Okay. So just to repeat the difference between these 2 points of view, because often they're sort of a bit, well, entangled. I want to disentangle these two perspectives. So the first is in terms of the replica manifold. This replica manifold has branched points and conical singularities at the boundaries of your interval. And in the second perspective, we're just still working with the same worldsheet, which you can think of as the orbifold manifold, meaning the replica manifold quotiented over the Zn symmetry, if you come from this first perspective, okay? And of course, this worldsheet is smooth. It's just the plane. So there's no conical singularities at the A. So if you have, in the picture where you have twist fields, there's no conical singularities, because the twist fields take over the role of imposing those gluing conditions that you need, okay? So all physics now is in the presence of the twist fields. Okay, so this is also a very useful perspective, because now our Z of n is a correlator, and when we discussed CFT, we discussed the invariance of CFT correlators, and how actually in two different ways you can express that. So these are things that we can use now. Let me not redo the whole derivation of the entanglement entropy from this perspective. If you're interested in that, you can read about it, for example, in the review by Cardi and Calabrese of 2009. But without going through the full derivation, let me mention how you can evaluate this correlator, okay? So in 2D CFT, a two-point function has the standard form, which is this 1 over the distance between the operator insertions to a power 2 to the dn, where dn is now the scaling dimension of those operators that you're taking the correlator of. So scaling dimension is what I called delta before, but I'm going to follow the notation of Cardi and Calabrese of using d sub n for the scaling dimension specifically of these operators. So you're assuming that these two have the same scaling dimension, and you're assuming by writing their two-point function as such that they are primary fields, okay, with some scaling dimension. So if you remember, primary fields are labeled by these two conformal weights, which together form the scaling dimension, okay. Okay, so we simply have that z of n is 1 over the length of the interval to the power 2 times the scaling dimension of those twist operators. And we know from our derivation from yesterday, from the replica manifold perspective, we know what this z of n in terms of L is. That was the whole point of yesterday's calculation. So from yesterday, we know that we arrived at z as a function of L as such, 1 minus 1 over n log L. Like this. Which means if we compare it to this twist field correlator interpretation of this object z of n, that we can read off what the scaling dimension of these twist field operators is. Namely, we can read off that they have a scaling dimension which is c over 12 n minus 1 over n. So there's an alternative way in which you can determine these without knowing the answer from using a ward identity, but let me not spend time on that alternative derivation so you can find it there. So, but the point is, from this perspective, you get the same result for your entanglement entropy, c over 3 log L over epsilon. From this correlator interpretation of z of n. Okay, I'll make some space for the conclusion on this. Yeah.
Can we build this twist fields out of the phi fields somehow? Or how do are these twist fields already in the CFT that we've looked at?
No, I don't think there's a way of seeing it like that. It's more like external fields.
Okay, then how?
That you define to have this, yeah.
Okay, but these external fields do not spoil the CFT, the conformal symmetry.
No, well, the point is that you can assume that they are primary fields of the CFT, and then that is consistent with the derivation. So you take that as an okay, my assumption was right, and they are primaries. But there's a whole literature on these twist fields in the context of symmetric orbifolds that I don't know. So what I said just now is how I interpret it from this context. Okay, these exist beyond this context, and there will be much more to say about that. Okay, so there's a reason why we went through this to this other perspective, and that's because it's useful to conformally map our entanglement entropy results to conformally related geometries. And that's because we can use the invariance of correlators, which we spent some time on yesterday, can be written as in terms of their value in conformally related geometries, okay? So that's what I want to spell out now. Let's start with the conclusion. So for the following setup, namely, so I'm rewriting the conclusion because I'm going to slightly change the notation. Okay, so the setup is a CFT on a planar background, dx squared plus the Euclidean time squared for our complex plane. Yesterday, I wrote that in complex coordinates as d zeta bar. But then also at some point, I used zeta to run over the whole replica manifold. So here in this context, I decided, okay, let's use f for x plus I to e. So f is now my complex coordinate on the plane, on C. And we've been worried about the entanglement entropy for an interval A when the CFT is prepared in the vacuum state. So the vacuum state, you could write as 0 like this, but really you should tell me if you're saying the vacuum state, you should tell me with respect to which coordinates, because the vacuum state is a zero energy state. So I'll want to know what your measurement of time is to understand what you mean by the vacuum state. So that's why I'm including the subscript here. So it's the vacuum state as measured in f coordinates, meaning zero energy with respect to this time. Well, so with respect to time t. Okay. So for this setup, we find that the vacuum interval entanglement entropy is given by SA equal to C over 3, the log of the length of my interval over a UV cutoff. And so now I write the length of my interval as absolute value of F1 minus F2. And I include in the UV cutoff, again, a subscript that this is the UV cutoff in these F coordinates on the df bar metric, okay? But it's really the same result as before, so where I just had log of L over epsilon, okay? So this is my conclusion that my entanglement entropy is C over 3 log L over epsilon, which you can derive from knowing Z of n being the correlator of twist fields equal to the length to some power which we determined there by knowing the scaling dimension, okay? Okay, and so as I said, the advantage of this target space derivation, well, I left out the actual derivation, but let's say perspective, is that once you know the correlator, the correlator of the twist fields on the plane, you can conformally map it to the correlator of the twist fields on some conformally related geometry. Okay, this is one. So these are just Z of n, and you know that once we have Z of n, we just plug it in the definition for the entanglement, and we know the entanglement. So if this is true, that you can conformally map the correlators, you can also conformally map your entanglement entropy to give you the entropy in a conformally related geometry. Okay, so as I said, to do this mapping of the correlator, what we're using is this, I called it so the second version of expressing conformal invariance of correlators in a CFT. That was on the board yesterday. So in that general notation, we had something like this. Okay. So this we can now apply to our twist field correlators. So let me write the right-hand side here because I ran out of space, but it's equal Okay, so just literally applying this, which was called 2 prime, I think, expression of conformal invariance. You apply this to the twist field correlator, which is the twist field correlator, which has a conformal dimension dn, which we know in terms of the central charge of the CFT. Then the twist field correlator on the F plane is related to the twist field correlator on some dz bar geometry, which is conformally related, so by a Weil factor to the planar geometry by this expression, okay? And so, for example, a typical conformally related geometry to the plane is a cylinder. And then you can do a map from here to here, and then find the entanglement entropy for an interval on the cylinder very quickly, okay? Okay, I'm just spelling out now here in this last line what I said here about the conformally related geometries, okay? So the F-plane is related to, for example, the Z-cylinder with this Weil factor. Okay, I'll need more space. So next, I'm just going to write out very explicitly, if you have a conformal transformation from F to Z, so you have some conformal transformation. Remember, we said in 2 dimensions, any transformation of this form is a conformal transformation, because it just gives you a Weil factor df over dz squared. So I'm now going to write out very explicitly, if I give you an f of z conformal transformation, what is the formula that you can just, for the entanglement entropy, that you can just plug this f of z in and you know the answer, okay? So it's useful to have that explicitly, but nothing really is happening. I just have to write all of it down. Okay. So this is just writing out the Weil factor in terms of f of z. Next is just to write down SA. So let's see. And you can split it in a left-moving and a right-moving part for the F and the F bars. So let me do that. So here in this step, from the top line to the next line, you can read this off from this conclusion. So if your correlator is something to that power, then your entanglement is log of that something over the epsilon. So it's that something here now that is the combination that appears in the log, in the general entropy formula. Okay. Okay, so there's two remarks to make about this. So in last line, like I said, I just split into left movers and right movers. And you'll see that I introduce now a new epsilon, which is the epsilon measured in the z-coordinates in the dz bar geometry. So there's two remarks to make about this. The first is precisely about this new UV cutoff. So if you compare the general formula for entanglement entropy, so this is now the general formula for entanglement entropy for an interval in the dz bar geometry. The UV cutoff that appears here and the UV cutoff that appears in the planar formula, they're related by this factor here, but if you symmetrize it over an epsilon at the left point and the right point of your interval, the relation between the UV cutoffs is that the one in f coordinates is f prime of z times the one in z coordinates. And that makes sense just from Taylor. So that you can write f of z plus epsilon z minus f of z as epsilon z f prime. So if you would call this a small delta z distance and this object a small delta f object, delta f distance, which you could call epsilon f, then you find this relation. So this is another way in which you can remember this denominator in the entanglement. Okay. So that's the first remark. I have 1 minute left for my second remark, which is good. That works. So the second remark is again about the combination that appears now in the log, including this denominator with the square root of the f factors. Okay, so sometimes I'll use u and v instead of x1 and x2 for the endpoints, okay? So this combination is a global conformally invariant combination. Meaning that if your conformal transformation f of z is a global conformal transformation, so belongs to this subset of Möbius transformations that I mentioned, so translations, rotations, etc. In that case, this object is again equal to just u minus v. Okay. So this is only true for f of z of this form, so a Möbius transformation. So an example of this is one of the transformations we did yesterday from the interval to the half line. If you check it again, the transformation that we used was precisely of this form. And this makes sense because a global conformal invariant combination leaves the state of your system invariant. So it leaves you in the vacuum. Okay, so let me write it like this, but you don't have to understand this notation if you're not used to it. But if it leaves the state invariant, it should also leave your entanglement entropy for the vacuum state invariant. So your von Neumann entropy for the vacuum state will then also be invariant, meaning u minus v over epsilon becomes fu minus fv over this new epsilon, but it remains the same specifically for Möbius f. Okay. And the state invariance is also reflected in the vanishing of the Schwarzschild for this type of Möbius transformations, for this type of conformal transformations, namely Möbius transformations. So you won't have this C over 12 times the Schwarzschild addition to the stress tensor transformation rule, meaning that for a global conformal transformation, you will also have that TFF equals TZZ. And this is another way of seeing that the state remains the same under this type of transformations. Good. So one example of making use of that formula upstairs for the entropy in a conformally related geometry is to write down the entropy for an interval on the cylinder. And this I'll move to the exercises. But really you can just find the right conformal map and plug it into this formula. So then after the break we can continue with the thermal interpretation as yet another interpretation of this entropy that we've been discussing, but which is important for the holographic interpretation as well. So let's reconvene at 1:45. Yeah. Okay, so next is another perspective. There's many perspectives, but each of them is helpful. And this one is helpful also specifically for the holographic entanglement entropy that we'll discuss later. So here I want to discuss the relation to...
It's fine, it's just the blinds.
Okay. The relation to thermal entropy. So you can think of this as a shortcut for deriving the entanglement entropy. And as I mentioned, I partly want to introduce it because it's important for the holographic interpretation. So the main reference I'm going to follow here is the original paper by Halsey, Larson, and Wilczek. now that I'm giving references, I remember that I forgot to mention a useful reference for this passive to active point of view of coordinate transformations. So for that, there's some notes by Bertschinger on GR. So from MIT. So, and these ones are useful for this active versus passive from yesterday, okay? I just forgot to mention it then. Okay. So first I need to explain that you can think of a partition function for a thermal QFT as a path integral over a periodic path. So since I'm not sure whether everyone's familiar with this, let me quickly explain it. So in a thermal system, any thermal system, you would have a partition function like this, right? So you sum over the microstates. And so similarly in a thermal QFT, you will have some partition function, which is a trace of e to the minus beta h, or the trace of rho thermal, we called it actually, which is thus taking the trace of this thing, so the phi A component of the thermal density matrix, and then integrating over all values. That's just giving you the trace, okay? So if I write down the partition function of thermal QFT, I would write down this. And the statement now is that you can recognize this formula as a Euclidean amplitude. So for that, let's write again a Euclidean amplitude like we did in the first class in the Schrödinger picture, Heisenberg picture, and path integral picture. Okay. So actually, let me do it first for quantum mechanics. And I'm going to use this analytic continuation of my time to define the Euclidean amplitude, okay? So this means that in the notation of the first lecture, I'm taking theta equal to minus pi over 2, okay? Okay, so as I said, this is again the Schrödinger versus Heisenberg amplitude versus path integral interpretation of that amplitude. So this is exactly the same expression as we had on the board in the first lecture. Let me now trace this expression. So I trace it, meaning I take this q to be the same as this one, and I integrate over it. Okay. Okay, so in the three pictures, this is what I have. I trace over this, I trace over this. And here I then have my path integral from Qi after a Euclidean time big U, I'm back in Qi, and I trace over those values. Then in total, sorry, I'm missing my e to the minus I here. So in total, what I have here on the right-hand side is some path integral over all possible periodic paths between Q of length U between Qi at 0 and Qi at U. Oh, apologies. That, yeah. But for with any possible value Qi. So let me write it. So you want all the paths that are periodic. So which can be any possible Q here, Qi here. Okay. So this here on the right, what you have is a path integral over all periodic paths (0 to U). And what we have on the left is the trace of e to the minus UH. Okay. Happy or no? Okay, so this was for quantum mechanics, but I'll just apply it now to quantum field theory. So now going to QFT. I'll just write the same line. Let me already call this U beta for obvious reasons. And then I have that this trace is equal to, okay, never mind about the Heisenberg picture. I just go straight to the path integral picture. I have integrating with these initial and final boundary conditions. So together, this integral is just the path integral over all possible periodic paths. Right. So what we find just from knowing that the Euclidean amplitudes are path integrals, we find that the trace of this Euclidean amplitude, which is precisely what gives us the partition function of a thermal QFT, is given by a path integral over periodic paths of length beta in Euclidean time. So if I interpret this left-hand side as a partition function of a thermal QFT, then beta here is my inverse temperature of that thermal QFT. And here on the right-hand side, in the interpretation as a Euclidean path integral, beta is the length of a periodic path in Euclidean time. Okay? So what we have found, let me stay on the left to make that conclusion. Okay, conclusion is that we find that the partition function of a thermal QFT is equal to the Euclidean path integral. So of a thermal QFT at inverse temperature beta is equal to the Euclidean path integral over all periodic paths in Euclidean time of length beta. Okay. So that another way of saying this is that compactification of your Euclidean time, so U is your Euclidean time direction, compactifying it with a period beta is like turning on temperature in your QFT. Okay, or should I write it in words or, yeah. Okay, so now let's go back to our entropy story. So let me write our vacuum state that we are working with. So as we've been doing before, we write our state in this pictorial way as prepared by Euclidean time evolution. So I'm going back to my 2D CFT bipartitioned in an interval A and the rest. Yes?
Sorry, I have a question from the last part.
Yeah?
So what happens to the boundary conditions when you go to the Lorentzian time?
Well, this is the whole point is the thermal interpretation is a compactification of your Euclidean time. You still have your Lorentzian time direction there. It's just, well, I'll make some pictures when we're in the thermal field double section that should make that clear, that first you can prepare a state, your Euclidean time preparation, then further evolve in Lorentzian time. Good. So back to our setup with for the entanglement entropy. This is our vacuum state of a 2D CFT prepared by Euclidean time evolution over what I called Euclidean time and the x direction in this way for, let me call it now again zeta, okay, which was x plus I TE. This F notation was just because it was more useful for the mapping interpretation, okay. So this is our vacuum state in our 2D CFT, and we've bipartitioned this. So let me already choose my A to be here, so from 0 to L. Okay. This is my region A. So instead of having a random x1 and x2, I'm going to already translate it to start in the origin. So this is my region. So I have my interval A, which was given by x equal to 0, L. But then at the end of our calculation of the entanglement, we saw that actually we had to introduce this UV cutoff because the whole thing is divergent and you want to regulate it. So actually, let's consider our entanglement, our interval A, to start at this UV cutoff epsilon and end at L minus epsilon. So you put a symmetric UV cutoff at each endpoint of your interval A, okay? So I remake my figure for this to be epsilon and L minus epsilon, okay? So that, actually, I'll draw it a little bit bigger. So I have 0 somewhere here, then I have an epsilon here, an L minus epsilon here. This is my region A. So let me not write A, but A is always the red region. Good. And then the complement I'm going to draw in green. So the complement will be a bar in green, and the interval in red is A. Okay, so this is just the same picture that, that we had before in my zeta plane for the preparation of the vacuum state. So this dashed line is still here, but it's a bit hidden behind the colors now, okay? Okay, now let me do some conformal mappings. So I'll map first from zeta to W. This is actually the same W that we had yesterday. So the effect of this mapping is just to send L, so the right endpoint of the interval to infinity. That's all that this mapping does. And the rest stays here. But let me draw infinity now already in polar coordinates. It will become clear why I'm doing this in a second. So now this is the W plane. I've chosen now to draw it in polar coordinates. And let me track where my intervals is going. So it's transformed now into the half line. Where let's say first, before we introduced the cutoff, we had the interval 0 to L is now mapped from 0 to infinity. Okay. As in 0 is mapped to 0, L is mapped to infinity by that map, zeta to W. And then if I do it carefully, with the UV cutoffs in place, what I actually have is that my region A is W taking the values epsilon over L and L over epsilon, which goes to 0 and to infinity, okay? I'm just plugging epsilon in here and then plugging L minus epsilon in here, okay? So let me write the region A here. So this is why there's a little cutout here around the origin. So I start here at epsilon over L and I end at L over epsilon. That's my region A. And region A bar is this other half here, okay? Okay, so this was actually the same mapping that we did yesterday in the context of the replica trig derivation of, or replica manifold derivation of the entanglement entropy. And then what we did next was, yesterday, was to take W to the power 1 over n, and we called that Z to go to the orbifold. That's not what we're going to do now, so I'm going to introduce a new Z now, which is a different conformal map. So now the next map is going to be that I take Z to be equal to 1 over kappa, the log of W. So kappa is now just a number that I'm introducing. It's an arbitrary real number that we introduce in this conformal map. So since it's arbitrary, we'll need the physics to be independent of kappa, okay? So what this will do, this map, is map the red line, the red half line, onto a full line that runs from Z is minus infinity to infinity. So again, let's do it carefully with the cutoffs. We have that this endpoint W is epsilon over L, is mapped to 1 over kappa, the log of epsilon over L, okay? And we have that W is L over epsilon at the endpoint. It's mapped to 1 over kappa log L over epsilon, okay? Which maps to which is minus infinity and infinity in the limit of the UV cutoff going to 0. So we have a full line. I can already draw the full line. From 1 over kappa log epsilon over L to 1 over kappa log L over epsilon, which is now my region A. Okay. What about region A bar? It runs from 1 over kappa the log of minus epsilon over L to 1 over kappa the log of minus L over epsilon. Okay. Now let me write the minus as e to the minus I pi. Then I have that this is 1 over kappa log epsilon over L minus I pi over kappa for the beginning of region A bar. And I have here 1 over kappa log L over epsilon minus I pi over kappa for the endpoint of region A bar, okay? So if here I'm drawing the complex plane Z, then my A bar is a distance pi over kappa away in the imaginary direction from the A region. So I have 0 here, and I have minus I pi over kappa here, so that my region 1 over kappa log epsilon over L minus I pi over kappa to 1 over kappa log L over epsilon minus I pi over kappa is this region, okay? So this looks again like my top figure because I'm again thinking of z as some x plus I time, but I need to introduce new coordinates because they're of course different from those x and Euclidean time. So I'll call that x sub z and tau, okay? So I have my tau running upwards in this figure and my xz in this direction in this figure, okay? So this is now the dz bar plane, and this is where my A and my A bar are after all these conformal mappings. Okay. The point is that what we've achieved by this is that region A is now completely on one side of this strip. So A is now one side of a strip of width pi over kappa. Okay. Now, let me add in these pictures, because I've introduced two different Euclidean times. I have the z time tau, and I have the zeta time t sub e. Let me draw those directions a bit more explicitly in some color. To remember where each Euclidean time is in this story. Okay, so here Euclidean time is going up, so let me draw the zeta Euclidean time with these small blue arrows. And this is the time that points towards the dashed line, as in it's the Euclidean time that we used to path integrate from the infinite past to the zero slice to prepare our vacuum state. So it's pointing at the dashed line, which is where our state lives. Okay. So everywhere in these pictures, this is where it has to point, to where the dashed line is. So if we just follow these conformal maps, here it would be these lines that point to the dashed time slice. And here we would have some going like this and the others going like this because our dashed lines have split. Okay, so what I'm drawing here is the Euclidean time direction, which is the Euclidean zeta time, and it runs in the direction of the path integral evolution that prepares from minus infinity to 0, that prepares your vacuum state. Okay, and now let me use green to show where tau is on each of these pictures. Tau being the Euclidean z time. Okay. So, well, here in this picture it's obvious because it's the time-like direction in this picture. So tau is going this direction, and so that means that you see that it points from where the region A bar is in green to the red region A. This is the direction of this arrow. So we just follow this direction of this arrow to also write it on the, to also show where it is on these pictures. So here it would be this line. Here it would be this, some angular direction that rotates around the endpoint of the interval in the original picture. Excuse me?
If it's pointing from a complement to A, then shouldn't there be also another arrow to?
Yeah, there would be also one there. Yeah. But I'm mainly interested in this point because I've sent that point to infinity. So the arrow that I'm keeping in these other figures is the one that I'm drawing here. Okay, so this tau evolution we can remember as going from the complementary region to our region A in the state psi. Okay. Now let me look at the inverse map here. So I wrote this map from W to Z as Z being the log of W. So then, of course, the inverse map will be the exponential, but let me write it out. So the inverse map will be W is e to the kappa Z. Let's continue this there in that corner. Okay, kappa was arbitrary, so let me first set it equal to 1. So that map says that e to the real times z times e to the I, the imaginary part of z, is equal to w. So that means that in polar coordinates, this here is the radius of my w plane. And the imaginary part of z, which is precisely what we called z time tau, is the angle, the polar angle. Of the w plane. So just as a check, this makes sense with the direction of tau that we drew on here, going from A bar to A, right? So this is just what we're reading off from the conformal map, is that tau is the polar angle on the w plane. Okay? So actually, I'll introduce another notation, which is that this radius I can call large R times e to the I tau, okay? So now you see why I decided to draw the w plane already in polar coordinates, because it's sort of a step in between going from that plane to the z notation, with w in polar coordinates being this e to the real part of z times e to the I tau. Okay. Right. No, I want to stay here because let me actually bring back kappa. So if I bring back kappa, there's kappa here, there's a kappa here. And there's a kappa here. So before I brought back kappa, it's clear that this tau has a periodicity of 2 pi because it's sitting in the exponent of e to the I and times tau. Okay, so because tau is appearing in the imaginary exponent of the exponential, it's clear that tau has a periodicity tau plus 2 pi. This was for kappa is 1. And so if we bring back kappa, then we have that tau has a periodicity of 2 pi over kappa. So let's check with our figures that this periodicity makes sense. So I told you tau is not only the z Euclidean time, but it's also the polar angle in the W picture. And there, your polar angle should have a periodicity 2 pi. Okay, fine. In the lower picture, I should have that my tau has a periodicity of 2 pi over kappa. So what I wrote, the way we drew this this picture here on the lower board is as a strip. A strip of width pi over kappa. But now that we understand that this tau has a periodicity because of this exponential map, it's clear that tau has a periodicity of 2 pi over kappa. This suggests another visualization of the strip where you see this as half of a periodically identified structure, okay? So, meaning the cylinder. So let me try to draw it. So I have the green area, the green A bar region on the back, and I have the red A region on the front, okay, of my half cylinder. So this, this is a revisualization of this picture of the strip as half a cylinder, so that if you would go around the whole cylinder, you would have a periodicity delta tau equal to 2 pi over kappa. Okay, because from the red part to the green part is the length pi over kappa in the tau direction. So the tau direction I put in this color. So tau direction is now going this way. And in this visualization, it's much more clear that tau is a periodic coordinate. Okay. So I have tau going this way. If you want, actually, I would have to put this stuff that shows me that I'm path integrating over this structure, okay? So if you want, I can now also bring back the zeta Euclidean time, okay, which is these small blue arrows. And it's also clear that this visualization is superior to the left one in that sense that it brings back how you think of the path integral evolution from the past to creating the state on the dashed line at some time. Okay. So in the sense that this visualization remembers the direction of the blue arrows preparing the state. Let's see. Right, so let me now write the metrics that are involved in this story. So these are all conformally related metrics. because we're doing conformal maps in between. So the ds squared of the strip or of the cylinder is the dz bar. Sorry, yes?
Just a question on that diagram. So that I might be confused, but given the fact that tau in all the earlier diagrams points from...
Ah, sorry, yeah, yeah. Yeah, no, you're right. Let me see how I had it on my picture. Yeah, I had it right on the picture, but I drew it wrong here. Thanks. So the direction of tau, the way I drew it, is this direction. Okay. Yeah, thanks for the correction. Right, so discussing the geometries now. So the ds squared of the last picture, did I actually name them here? I wanted to name them A, B, and C. Okay, so C. A and B. Okay, so the metric in the last picture is dz bar. Okay, it's easier most of the time to think of kappa as 1. So for kappa it's 1, this is just d log w bar. So this will bring out a w and a w bar in front in the denominator. In front of a dw bar. So this is now indeed a conformal factor times our w geometry. So we can map that to the w metric in the second picture, which is dw bar. I wrote I drew the second picture in polar coordinates, so let us do that here. So in polar coordinates, meaning writing w as r e to the I tau, this w plane is dr squared plus r squared d tau squared, okay. And in this notation, the dz bar strip is dr squared over r squared plus d tau squared. So here you're using z is log r plus I tau. Okay. Yeah, so if you want, it's dxc squared plus d tau squared. Okay, so this is going backwards, let's say, from the last geometry dz bar to the middle geometry dw bar, and then finally going back to the zeta coordinate, we'll have some conformal factor in front that we can drop, because this is, for example, a time where I would say the CFT does not care about this while factor. And you end up with the first geometry in the first picture. Okay. Good. Okay, so like before, once we have these are all the pictures for the wave functions, so for the states, sorry, so for the psi's. So then next I can write pictures for the density matrix. Yeah. Sorry?
Time, so maybe, I'm not sure, would you say
Ah.
this is a good time to stop, or do you want to
Right, did I go over time? So it's 9:30 to, 10:30, 11:30. Yes, we could stop here because drawing all these pictures, yes, then I'll have to stop here. But okay,
If you need wieder 10 minutes, I guess that would be fine.
4 minutes? Well, so I think in 4 minutes I can. It's my suggestion because I need these pictures. So otherwise I would have to draw them again. Okay. So let's just quickly do density matrix for these for all these cases. I won't draw them as nicely or large as these others. Okay. Wait. So the first two ones are the simple ones, just the same as we had before, the plane. But then, so this is B, A. But then in the last picture, we have two strips. So I'll write the density matrix both as the strips or as the cylinder, okay? So using those two visualizations. So I have this strip, and then I have this strip, okay. Here are all dashed lines, okay. So just like always, to write the density matrix, you're just taking your cat and you're mirroring it around the TS0 slice to also include the bra. This is all I'm doing. So I had my picture here. So I moved the cat actually to the top and this one to there. Okay, so the ones in the Z geometry are a bit harder to draw, okay? So let me do the cylinder. But there's nice pictures in the notes. So if it's not clear on the board, you can check them there. So, okay, we have this one, this one. This one and this one. Yeah. Okay, let me not include the lines for the path integral evolution. Okay, so you just double all these pictures there to get the density matrices, right? But next, what you want to do is to write the reduced density matrix, which is traced over the A bar region, which is the green region. So I forgot to put my green regions in here. So we have red, and then we have green regions here and here and here and here, here and here. Okay. So let me try to do that on the same picture. So if these were the density matrices, I'm now going to glue along the green lines to get the reduced density matrix as measured by an observer in A, okay? So here I'm gluing. And here I'm gluing. So again, I have this picture that we already know, which is just the reduced density matrix as this path integral evolution with a slit in between along A. So this is the one that we've been using for the replica manifold, etc. Here, we glue along this line. And we get this figure, okay. Here we glue along the green line. So that we now have a strip of length, each of these was pi over kappa, so we now have a strip of length 2 pi over kappa. Or we glue over the green lines in the cylinder picture, which means attaching the back ends of these half cylinders and gluing them together. Like so. So that now you have a cylinder of length 2 pi over kappa in the tau direction, but with a slit so that you don't actually close the cylinder completely. So this is rho A in the cylinder picture, and this is a very useful version of the reduced density matrix, and I can explain why next time. Okay. So let me stop there, and then we can continue with these last pictures of the reduced density matrices tomorrow.